you see this is CSI-Alps and chasing the Pleistocene glaciations. And of course, it's always a, like I can, okay, I can do it like this. No. Wait a moment, how I can proceed? Oh yeah, I got it. Okay, so this is a teamwork that has been done during the last more than 10 years. And you see it's, we have like a University of Bern, ETH Zurich, and of course our sponsors or like financing institution or organ is the Swiss Federal Nuclear Safety Inspectorate. And I saw with this figure, with this picture, you know, this is the Turnstone glaciers in the Canadian Arctic. And if you look at today, it looks like you have the mountains at the peak, at the background, and the huge Piedmont ice is on the foreland. And if you look at, then you have meltwater systems, channels, and so on. It is exactly the same situation for the Alps, for the Northern Alpine Swiss foreland, Northern Alpine foreland during the last glacial age and during the last glacial maximum. And we know that it is already it was the last time that the ice was in the Northern Alpine foreland. And if you look at now to this figure, so on the left hand side, if I can use this one, yeah, and here in this profile you see the summary of the quaternary stratigraphy of the Swiss Northern Alpine foreland. And if you look at here, the greenish yellowish colors are representing the youngest ones, so the terraces or glacial fluvial deposits which are belonging or attributed to the last glacial maximum and the previous ones. And if you go into this direction, you go higher positions, you have relict deposits which are sitting on the bedrock, and they are made of mainly glacial fluvial deposits with some till in it and some other material sediments. So this is a typical morphostratigraphic summary. If you go high in the topography, you go older. So it has this terrace stratigraphy has a reverse stratigraphic relationship. So if you look at it carefully, so you will see that there are like these green colors, and you go in the time, and then there are two phases of incision, and the summary of these is on the right hand side. So you see this is the extent of glaciers to the foreland during the quaternary, so during the last 2.6 million years. In the good old days, previously, these 4 stratigraphic levels, so TDS, HTS, and the HT and NT, were normally correlated to the classical Planck and Bruckner 4-fold glaciations. Like the oldest one, the Swiss Deckenschotter, the cover gravels, were attributed to the Günz glaciation. The lower one, the bluish colors, was attributed to the Mindel, and the greenish colors, the high terrace level, was attributed to the Riss glaciation, and the yellowish ones to the Vermeer glaciation. But in time, we realized, or it's shown that the glaciers were already at least 13 times in the foreland. So it's more than 4 glaciations. And one thing is here that I should mention is, if you go old in time, then our precision is getting diffused. We have less data, less age constraints. So it's getting much more difficult. That's why I have chosen the topic of CSI. It's like looking for criminals. Now, after this introduction, here is the outline of my talk. So first, we have also, besides the fundamental science questions, we have a societal impact when you chase the Pleistocene glaciations. Now, of course, afterwards, I will talk about the challenges that we have to tackle. Then, of course, some information about the tools that we were using during the last 10 years. And of course, then I will give you a summary of what we have been doing, especially for the most extensive glaciation and Deckenschotter glaciations in the Alps. And I will finish my talk with conclusions and outlook. Now, the societal impact is, Switzerland decided to build a deep geological repository for permanent, safe, and nuclear waste. Of course, the preconditioning is that the decay time is of this waste disposal is around 1 million years. So we require that these disposal do not come to the surface until they complete the decay. This means during the coming 1 million years. So of course, this such a long time requires that the layers overlying this repository should not be removed by fluvial or glacial erosion. Therefore, we are curious about reconstructing of the landscape evolution of the northern Alpine Foreland during the last 2 million years for a better planning of the nuclear waste disposal. Well, some challenges are we use, of course, present is the key to the past. So during the glaciation times, especially during the Deckenschotter glaciations, it was the same as similar today. So it was a transient landscape. So in interglacial times, lakes act as a sediment traps. So what you need is, if you want to bring fresh sediments from the Alps to the foreland, you need to have glaciers. So this means if you look for, if you can determine the freshness of your sediments or source of the sediments from the Alps, you need to have like a foreland. In stratigraphy, of course, we have a problem because terrestrial settings, as you may know, lithostratigraphic and morphostratigraphic units can laterally be continuous, but they might be chronostratigraphically discontinuous. This means if you move laterally, and even if you stay in the same petrographical composition, it doesn't mean that you have the same time of deposition. So this is one of the challenges. Then, of course, deep erosion, such as glacial erosion, incorporates clast from the upper several meters of bedrock. Then, of course, glaciers transport these clasts, and then you have, in addition, that reworking of the previously deposited material. And of course, the sediments are transported either subglacially or englacially from the Alps, and they come to they are deposited in the foreland, but they do not come to the surface unless they are supraglacially transported. So what happens is all the gravels that we are looking now on the northern Alpine Foreland are once brought to the foreland by the glaciers and then distributed by the meltwaters or the river systems and finally deposited. So the tools that we have been using are mapping and stratigraphy, classical tools in the field. Then we do class petrography. So then one can say about the catchment area, transport route. Then we measure the morphology of the classes. So then you can talk about the transportation and deposition. Then class fabric, if you can measure, then you can determine the flow direction. And of course, what you need is time. When you can determine the time, then you can talk about the timing, frequency, and magnitude of the events. Examples. So here you see wait a moment. Yeah, you see a beautiful plate for examples from clasts that have been cut. So what you do is you go to an outcrop, you identify the quantity of the different lithological lithologies, then you can make you can characterize your deposit. Then what you can do is you go and select the same lithology and you measure the flattening index and the roundness index. And when you plot the flattening index versus roundness index, then you can say that whether they are predominantly glacial deposits or predominantly fluvial. So you can then estimate, if you have, in case of glaciofluvial, then you can relatively estimate the distance to close to a glacier, far away from the glacier. So these are really robust and relative determinations. And here is an example of a class fabric. So these are our students in a gravel pit looking to the LGM till, and they are measuring the flow direction of the ice that deposited this LGM till. Then dating, of course, if you don't have dating, then it will be really difficult. This is an example of what is. This is a table showing the different dating techniques that are applied in quaternary sciences or quaternary geology. And on the right, on the horizontal axis, you have the time in logarithmic scale. And here I marked the limit of the radiocarbon dating with a black line. So if you go older than beyond the radiocarbon, there are not many options that you can apply for quaternary, especially Pleistocene, middle to early Pleistocene deposits. So, and in red, you see the cosmogenic nuclides. I will give you some information about the cosmogenic nuclides. This is a beautiful cartoon which appeared this year in a publication, in a review publication. So what happens is our Earth is continuously bombarded with cosmic rays, and the cosmic rays, they enter to the atmosphere and they react with the elements such as oxygen and nitrogen or in the atmosphere, and they collide, and there is the formation of tertiary and secondary cosmic rays because of these collisions. Then if they enter to the mineral lattices of the if the crystal lattices of the minerals, then you have the formation of cosmogenic nuclides. There are different applications that you can see in this cartoon. I won't go into the details of this, but if you look at here, then what you could do is you can go for boulders or for surfaces. You can do surface exposure dating, then you can go for deposits with the burial dating. So how we can date geological layers or deposition time of gravels? So what you could do is you can use the buildup of the different nuclides, and you need to have a surface top layer at a geological layer at the surface. Then you can get at least 4 samples in a layer, and then you can measure the concentrations. And we all know how the concentration or the production of the cosmogenic nuclides changes at depth. Then you can calculate and you can model an age. But here is the problem: you have 3 unknowns like the time, inheritance, and the erosion rate. So inheritance you can estimate, but then you are strongly dependent on the erosion rate. To tackle this, what you could do is you can do burial dating. So you can use the decay of the cosmogenic nuclides. So in that case, you need 2, aluminum and beryllium. In quartz, for example, you go in a deep place or deeply buried deposit, you get your sample, you measure aluminum and beryllium concentrations. If you can do that, you can get the age of your deposits. But however, it is you have a requirement that you have no post-burial production, and then you have to have a saturation of cosmogenic nuclides before the burial, and you cannot have reworking. So in this, that's why I think we violate this in the glaciofluvial deposits, especially when you have glacial erosion. So to tackle this, we have isochron-burial dating. Again, the decay. What you do is you go for the same isoline, isochron, and collect samples. So for example, here we have 5 samples, 5 clasts. What you do is they all lie at the same position. So this means they have all the same post-burial history, but they might have different pre-burial histories. Using this, you can measure, plot your aluminum versus beryllium ratio, then you can regress a line through your data, you calculate a measured ratio, and after you model the the production, post-burial production, then you can calculate an initial ratio, the ratio at the time of deposition, and using this you can calculate an age. So now let's go back to northern Swiss Alpine Foreland. You remember this stratigraphic, morphostratigraphic configuration. Let's start with the LGM. So this is the LGM map of Swiss Alps during the LGM, during the last glacial maximum. And you see the ice being in the foreland. It is morphologically well constrained. There are a bunch of radiocarbon ages. So it was, the timing was already known, even the development of surface exposure data. But if you go back in time, now we go to the Merlin glaciation. This is the similar map of the Swiss Alpine Foreland during the glaciations. This is made by Roman Frey at 1912. And you see these are the maximum extent of the glaciations, which is attributed to the most extensive glaciation. Now I will take you to this spot here, to the nose of this Rhine River. And here we are. So this is a geological map of the area at this point. So the blue and violet colors are the bedrock here. Then you have the Deckenschotter deposits, the old ones. Then you have these low and high terrace deposits here, which is overlain by a loess layer. And these dashed lines were attributed to the terminal moraines of the most extensive glaciation at the time, but recently it's found out that it's not the case anymore. But here you have a spot where we have a gravel pit, and if you go into this gravel pit, if you look at these, we have an old inclined layer of till, which is attributed to the most extensive glaciation. So our PhD student Katerina Dieleman did sample these, and first she attributed, or she counted the clast. So what she found out from this pie chart is that the 70% of the material is in this gravel pit is coming from the Alps. So it's an alpine origin material. Of course, the question was, if I go back to also that there was like a glaciers which were arriving from the Black Forest in Germany. So this was the reason to see how these petrographical composition. So we suggest that it was already 70% is alpine. So it was an alpine glacier coming to this location, and we also dated this. This is the isochron plot of this till in Merlin, and this is the aluminum concentration. This is the beryllium concentration. These are the measured concentrations, and we regressed the line and calculated an age of 500,000 years for the most extensive glaciation. So this was the example. Of course, as I mentioned, you have no geomorphic constraints. There are really relict sediments which were preserved that you can find. Now we go back in time to early Pleistocene. So originally, you see these are the red color and blue colored deposits which were separated with an incision and morphostratigraphically. And then there are at least 4 glaciations or up to 8. And then this has been, if you look at today's map, most of these deposits are beyond the LGM extent. And look at the brownish or reddish colors are the deposits. And they are flat tops. So they cover the bedrock, molasse bedrock or limestone, limestone bedrock. And they are mainly flat-topped mesa-style plateaus beyond the LGM. And there are places which are also overridden by the LGM. How they look like in the field, this is a view from the Rhine. This is the Lake Constance, and this is the Rhine River coming out. And then if you look at here, it's a flat top hill here, and then you have the deposits. And this is the same from this one. So you have the Molasse bedrock here. You don't see, of course, in the forest. And then you have these thick layer of gravels, which are forming these flat parts. Now, I will take you to, let's go to this, one of the famous ones here, Irchel. This is the most extensively studied part of these deposits, of these Deckenschotter. And here is the geological map. This, the brownish color is the Deckenschotter, these gravels, cover gravels. The blue line is the extent of the LGM, and the this color is the Molasse bedrock. So, and then you will see, there are two profiles. Let's go to and check these. So first of all, class petrography, it has been our PhD students Claude and Katerina Dieleman made lots of measurements of at different locations. And of course, they are too small, but if you summarize, there is one lithostratigraphical unit which has almost no crystalline components. So no crystalline components. Then there is another one where you have dolomites exclusively that is found in these locations, for example, here. Then the third one is a little bit a different one where you have third or fourth one. They are really similar, and the only difference is you have mainly limestones, some crystalline rocks, but the difference is on the quartz size or in vein quartz. But this is really, really two similar lithologies. And based on these, in 1993, Hans-Rudi Graf suggested this morphostratigraphy for the oldest, the highest Deckenschotter cover gravels deposits. And this is, I call it time lapse. This is what we knew in 2009. So, and in all these deposits, there is only one fossil found. So this is like mice mammal bones, which are attributed to the mammal neogene zone 17 to 2.5 to 1.8 million years. And it's here in this Hasler formation, which is attributed to the warm period. So you have morphostratigraphically 6 different units in this location. Now, then, of course, Claude started her thesis during her PhD thesis to study these. So we went to this location, 3 locations, and she made one depth profile dating here at Irchel and 2 locations in Hütz and Steig. And as you might see, the ages, Isochron-burial ages that we got are internally consistent, but they strongly contradicts the age from the mammal neogene zone. Of course, this was in 2019. Then Katerina started, and we went again to the same location, or sorry, before, based on the ages that we got, Claude suggested this morphostratigraphical profile that indicates a cut and fill system and no incision. Well, then in 2022, Katerina Dieleman went again to different locations again. So what we did is we went to the gravels below, to the Hasler formation at the other end of the thing, and then of Irchel, and then we found 2.6 million years, which is completely okay with respect to 1.8 million years. But then we really went down to this location and we dated again, and then we ended up with 1.3 million years, and all these ages are overlapping within 2 sigma uncertainties. And then we also went to the very first gravels that were deposited on the bedrock at Irchel, and we also got an age of 1.3 million years. And you see, it has locations where you have an agreement, but the ages are completely different than with respect to the with respect to the morphometry. Using these and combining all with the class petrography, Katerina Dieleman suggested that it was again a cut and fill system, which was a complex system with this configuration. Now, of course, when we started, it was 2009. Now we are these are the sites which has been studied, and if you look at all data, suggested published data or almost in press, all submitted data here, there are a bunch of, this is the aluminum-26, this is beryllium-10. Of course, this is not all our studies. There is also like different sites which were studied by NAGRA in Switzerland, and which is already published. And if you look at these, almost there are here more than around 130 data points, and they cluster around the origin. So this is the aluminum-26 concentration, this is the beryllium-10. If you zoom in here, you see that most of them are clustering around less than around 200,000 atoms per gram for aluminum-26, and something around less than around 30,000 atoms for beryllium. And here what I want to show you is also that you see there are really these yellowish colors here, bars are high, that are the uncertainties of aluminum-26. This is when we started to analyze first isochron-burial dates in isochron-burial dating in Siglisdorf in 2012, and actually it was 2009 and 10. And then look at the bluish colors. Now we are, do you see even the aluminum uncertainties in aluminum concentrations are less than the beryllium ones. So in these 10 years, what we did is we strongly improved our analytics to isolate the aluminum-26. And in addition, our colleagues at ETH Zurich in physics have a new machine which is called Milea, where we can really measure really low concentrations with low uncertainties. That's why we are really confident here that we can really measure really low low concentrations. Well, now if this is again the same map, let's look at what we have now all the time. So if you look at here, there are several sites that has been dated with isochron-burial dating, and we have also here Merlin, which is the most extensive glaciation. And if you put all this data on a profile, like the elevation about the river Rhine, above the river, this is the sites which are in the course, in the trajectory of the river Rhine, which belongs to the river Rhine river system, and on time. So you see these are the uncertainties of the age, horizontal axis, and the uncertainties of the top and bottoms of these gravel packages in different places. And if you see the deposition of these gravel packages do not change, or the elevation do not change through time, it's almost constant, then you have younger deposits, which are here, which are low, and then really young ones. So what this means, now let's look at the R river system to the west. Let's go to this part. It is, again, you see you have the old deposits here, and then it goes again, it concentrates around the Merlin glaciation around 500,000 years. And please do not forget, originally all these deposits are morphostratigraphically attributed to the Swiss Deckenschotter, the cover gravels, which are supposed to be older than 1 million years, even 2 million years. So now, after this, let's have a summarize. Here again, a profile along the two rivers, a river profile from west to east in the Alpine Foreland. This is the Aare River, this is the Rhine River, this is the Rhine Fall. And here are all the sites that belongs to the Rhine River system, which are dated. And this is the base level between 2 and 1 million years. Then this is a probable base level after 1 million years. So this means they belong to a cut and fill system, which are deposited from the beginning of Quaternary till the 1 million years. And then you have a distinct incision into the landscape. Then there is the deposition of the second one deposits. And in the Aare River system, it looks like it's a completely different system. And here is the Merlin. So to sum up, to conclude, so what we did find is we were able to identify at least 5 glacier advances during the Pleistocene. So 3 glaciations during the early Pleistocene, which are like 3 phases of gravel accumulation at 2.5 million years, around 1.5 million and 1 million years. Then a significant phase of erosion or incision after 1 million years, likely during the mid-Pleistocene revolution. Then the most extensive glaciation advance at around 500,000 years, and then another advance after around 250,000 years, which caused the deposition of young gravels in the Aare Valley system. And of course, what we suggest is glacially induced cut and fill architecture during the early Pleistocene, which still challenges the existing morphostratigraphy. Now, what we do next, of course, you know, we are still struggling with or contradicting with the mammal neogenes zone 17, which is found in gravels and in the Hasley formation. Therefore, what we do is we go for the below and above the Hasley formation. We do again sediment analysis. We do boreholes and sediment cores. We open trenches. We continue with geophysical investigations, and of course, we will continue for sampling for dating and look at this is the DM model of the Irchel area, and these are the yellow ones are already dated locations, and we will plan at least two boreholes. We'll core and get to see if this Hasley formation is continuous throughout this landscape, and if yes, if we find it, we will directly date it. Of course, here is a good example. So where we go until now, you know, if I could, our locations are always on 2D, and we never had a Isochron-burial, a chronostratigraphy in a profile. So therefore, we go back to the Vremel Irchel, where Anne-Claude had her depth profile here in these gravels. And if you look at here, this is a sediment package, gravel package. Here is the base. You have the Molasse bedrock at the base somewhere here. At this location, it's covered. Then you have the gravels coming, the first gravels on the bedrock. There is a gravel package. And here on the, which is on the line, red line, you have the Hasley formation. We think that it goes a little bit below the road here and until here. So you have a gravel package, then you have the Hasley formation, then you have a gravel package. So what we will do now is we will date above and below the information and see if we have the, then this, we will see the age in a profile. So, and then we will repeat this in at least in two or at least in two more locations at Irchel. So, and of course, Katerina Dilaman finished her PhD thesis, and she was so kind to give me some slides. So we already sampled. Here is the limit of this Hazli formation here at Irchel. She already took samples for isochron-burial dating. And with this, I would like to thank you for your listening. On this left-hand side, this is the first, a picture from our first field trip with Vasily Alfimov, our physicist, our brain, Christian Schlichter, Susan Iviox, when we were brainstorming how to date these beautiful deposits. And this is unclothed sampling at Irchel, and me and Katerina Dileman in a glacial geology excursion at Irchel with the students. Thank you.